Let me start with something that sounds almost wrong. When an object moves from one place to another, we usually think there is one path it takes. The ball rolls from here to there. The light travels in a straight line. The electron goes from point A to point B along some definite trajectory, even if we don't know exactly what it is. That feels obvious. So obvious that we rarely question it. But suppose I ask you a strange question. If a particle moves from point A to point B, how does nature decide which path to take? Not which path we observe, which path nature actually chooses. You might say, well, it chooses the shortest one, or the fastest one, or the one that minimizes energy. And historically, that's not a bad answer. For a long time, physics was built on exactly that idea. Nature is efficient. Nature is economical. Nature picks the best path and ignores the rest. Now, here's the uncomfortable part. What if that's not what nature does at all? What if, instead of choosing one path, nature quietly explores all of them? Not metaphorically, not poetically, literally, every possible path, the straight ones, the curved ones, the ridiculous ones that loop around, wander off, come back, overshoot, undershoot, zigzag like a drunk mosquito, and somehow still end up at the same final point. Every path you can imagine, and many you wouldn't think to imagine at all. That idea sounds absurd at first, and that's a good sign. Physics usually starts sounding absurd right around the moment it gets interesting. This is where Richard Feynman comes in. Not because he was the first person to think something strange, but because he had the nerve to ask a question most people would dismiss too quickly. What if the absurd idea is actually the simplest one? Feynman had a habit of doing this. He didn't start by asking what sounded respectable. He asked what worked, and if the working idea sounded crazy, he didn't mind. Nature, in his view, wasn't obligated to make sense to our intuitions. He once said that the test of understanding wasn't whether you could repeat the formal rules, but whether you could see what the rules were really doing. And when he looked at how particles moved, especially in the quantum world, he realized that the old story of one path, chosen by nature, was starting to feel like a story we told ourselves because it was comfortable. So instead, he flipped the question around. What if a particle doesn't choose a path at all? What if it takes all of them? At this point, you might feel the urge to object. Wait, you might say. That can't be right. If it takes all paths, why do we see just one outcome? Good, that's exactly the right objection, and Feynman didn't ignore it. He leaned into it. But before we go there, we need to slow down and build some intuition, because if we jump straight into equations, we'll miss the whole point. Feynman himself hated that. He believed equations were useful only after you knew what question you were asking. So let's step back and do something simpler. Imagine you're standing at the edge of a park and you want to walk to a bench on the other side. There are infinitely many paths you could take. Straight across the grass, around the trees, in wide arcs, in tight zigzags. You could even pace back and forth for a while before eventually reaching the bench. All of those paths are possible, but in real life, you pick one, probably the shortest, or at least something close. Now here's the key difference. In everyday life, you are choosing. You have preferences. You want to save time. You want to avoid mud. But an electron has no preferences. It doesn't know what's efficient. It doesn't know what looks sensible to us. It just follows the rules of the universe. So the real question is not which path does the particle choose. The real question is, what are the rules that turn all these possibilities into the single outcome we observe? That shift in perspective away from choice and toward process is where the path integral idea begins. And it didn't come from Feynman sitting down one day and deciding to be clever. It came from frustration, from noticing that the existing rules of quantum mechanics worked, but didn't feel explanatory. They told you how to calculate probabilities, but not how to think about motion itself. Feynman wanted a picture. a story that matched the math without hiding behind it. So he asked himself a dangerous question. What if the particle explores all possible histories, and what we observe is the result of those histories interfering with each other? At first glance, that sounds like nonsense. Histories interfering, paths canceling each other out. But if you stay with the idea just a little longer, something strange starts to happen. It begins to feel inevitable. Let's try a small thought experiment. Nothing fancy. Imagine you clap your hands once in a large hall. The sound doesn't travel along one single straight line to your ears. It bounces, it reflects, it spreads out in all directions. Some of those sound waves take direct paths. Others bounce off walls, ceilings, chairs, and people. Yet somehow your ears receive a clean, coherent sound. What you hear isn't the result of one privileged path. It's the combined effect of many paths arriving together. Now, sound waves are classical objects. We're used to thinking this way about them. But Feynman noticed something unsettling. Quantum particles behave less like tiny billiard balls and more like waves that carry phase, timing, and interference. And if interference matters, then ignoring most paths might be the wrong move. So here's the strange proposal, stated as plainly as possible. To figure out how a particle moves from one place to another, you don't pick a single path. You consider every possible path. For each path, you assign a contribution, a kind of weight that depends on how the particle would behave along that path. Then you add all those contributions together. Some paths reinforce each other, others cancel out. And what survives that grand cancellation is what we actually observe. This is not a metaphor, this is the calculation. At this point, many people misunderstand what's being said. They imagine a particle physically splitting itself, running down every possible path like a desperate multitasker, then reassembling at the end. That's not the idea. Feynman was very careful about this. He didn't claim particles really travel every path in a literal sense. He claimed that the correct way to compute their behavior is to sum over all paths. That distinction matters a lot, because physics isn't obligated to tell us what reality is in some philosophical sense. Its job is to give rules that predict what we will observe, and the path integral rules do that remarkably well. Still, it feels unsettling, so let's make it more concrete. Suppose you're rolling a ball down a smooth hill. Classical physics says the ball will follow the path that minimizes action, a quantity that depends on energy and time. You don't need to know the details yet. What matters is this: out of all possible paths, one special path dominates. Now imagine applying the path integral idea to this situation. You would consider all possible paths the ball could take down the hill. Most of them are ridiculous, looping into the air, teleporting sideways, or taking absurd detours. Here's the surprising part. When you add up all the contributions from all those paths, almost everything cancels out. The only paths that survive are the ones very close to the classical path, the sensible one, the one we're used to. So classical motion emerges not because nature chooses one path, but because all the other paths interfere destructively. That's a subtle but profound shift. Instead of asking, why does nature choose this path, we ask, why do all the other paths fail to contribute? And suddenly, classical physics looks less like a fundamental rule and more like a special case, a consequence of deeper quantum behavior. This was one of Feynman's great insights. Classical mechanics wasn't wrong. It was incomplete. It was what you got when the quantum interference patterns became extremely sharp. In other words, the classical path is not chosen. It survives. That idea alone is worth sitting with for a moment, because it changes how you think about explanation itself. You're no longer looking for a single cause. You're looking at a competition among possibilities where most lose. Feynman loved this way of thinking because it matched how nature actually behaves when you push experiments to their limits. Light doesn't travel in straight lines because it knows geometry. It travels that way because all the crooked alternatives cancel out. At this point, you might wonder where the math hides in all this. Surely there's an equation somewhere pulling the strings. There is. But we don't need to write it down yet. The idea comes first, always. Before Feynman, quantum mechanics already had powerful equations. Schrödinger's equation worked beautifully. But it told you how a wave function evolved in time, not how to imagine a particle moving. The path integral reframed the same physics in a new language, a language of histories instead of states, of processes instead of snapshots. And once you see it that way, something interesting happens. Motion stops being a line, it becomes a sum. Let's bring this idea down to earth with something you've probably experienced, even if you didn't realize it. Think about how GPS works. When your phone figures out where you are, it doesn't rely on a single satellite. It compares signals from many satellites, each arriving with slightly different timing. Your position is determined by how those signals line up. Now imagine if you ignored most of those signals and trusted only one. Your location would be wildly uncertain. Accuracy comes from combining many possibilities, not choosing one prematurely. The path integral works in a vaguely similar way. Each path contributes a signal, not a loud one, most are tiny, but together they encode the behavior of the system. Here's where the idea gets even more interesting. Each path doesn't contribute equally. It carries a phase, a kind of internal clock that ticks differently depending on the action along the path. Paths with wildly different phases tend to cancel each other. Paths with similar phases reinforce. That's why classical paths dominate. Around the classical path, small variations don't change the phase much. Those paths march roughly in step, reinforcing one another. Far away from the classical path, the phases swing wildly. Positive, negative, cancel, vanish. The universe, it turns out, is extremely good at canceling nonsense. This also explains why quantum effects are hard to see in everyday life. When objects get large, the phase differences become enormous. Interference patterns shrink to scales too small to notice. Classical behavior emerges not because quantum rules stop applying, but because they apply too well. This is one of those places where Feynman's thinking shines. He didn't explain quantum mechanics by adding mystery. He removed it. The weirdness wasn't a feature, it was a clue. Now, here's a common misunderstanding worth addressing gently. People sometimes hear about path integrals and think, oh, this is just another interpretation of quantum mechanics, as if it were a philosophical preference, like choosing vanilla or chocolate. That misses the point. The path integral isn't just a story you tell yourself. It's a calculational tool. In many problems, it's the most powerful tool we have. In quantum field theory, it becomes almost unavoidable. Feynman himself didn't care much for interpretations. He cared about whether the method worked and whether it helped you see what was going on. And it did. By thinking in terms of all possible paths, he was able to develop a new way of handling interactions, especially in particle physics. This led to the diagrams that now carry his name, simple sketches that encode complex calculations. Those diagrams weren't just bookkeeping devices. They were visual representations of processes, of particles, exploring possibilities and interfering. At this point, let's test your intuition. Suppose a particle has two possible routes from A to B, one short, one long. What do you expect? If the paths are very different, their phases will differ a lot. They'll cancel. You won't see interference. But if the paths are nearly the same length, the phases stay close. Interference survives. That's why interference patterns appear when alternatives are hard to distinguish, and why they vanish when information leaks into the environment. Notice how little we've talked about measurement. We didn't need to. The path integral handles motion without invoking observers or consciousness. It's about structure, not drama. This was another thing Feynman appreciated. He didn't want quantum mechanics wrapped in metaphysics. He wanted it grounded in calculation and intuition. By the time you reach this point, the idea that particles explore all paths no longer sounds quite as crazy as it did at the beginning. It still feels strange, but it's a productive kind of strange. And that's usually the kind worth keeping. There's one more misunderstanding that's worth clearing up, because it trips up almost everyone the first time. People often think the path integral says that every path is equally important. That's not true, not even close. All paths are considered, but not all paths matter. This is a subtle distinction, and Feynman was very careful about it. The contribution of a path depends on the action along that path. Paths with rapidly varying action tend to cancel out. Paths near stationary action survive. So when someone says the particle takes all paths, the right response is, yes, but most of them don't count. That's a very Feynman-like statement, by the way. Honest, precise, and slightly deflating. Another common mistake is to think the path integral replaces classical reasoning. It doesn't. It explains it. When you zoom out, classical laws emerge naturally. When you zoom in, quantum richness appears. The framework is flexible enough to handle both without contradiction. Now, let's try one more test of understanding by changing the context slightly. Imagine light traveling through water instead of air. It slows down. Classical optics says light bends to minimize travel time. That's Fermat's principle. But the path integral says something deeper. Light explores all paths. In water, the phase accumulation changes. The paths that reinforce are no longer straight lines. They're bent. Same idea. Different medium. The principle survives the context shift. That's a good sign you've understood something real. Feynman liked ideas that traveled well. If a concept only worked in one narrow situation, he didn't trust it. The path integral worked everywhere he pushed it. And perhaps most importantly, it changed how physicists thought about what a law of nature is. Not a command, not a choice, a pattern of interference among possibilities. That's a humbling idea. It suggests that the universe doesn't deliberate, it computes. But even that word, compute, is just another metaphor. Feynman would be the first to remind us of that. The universe doesn't run equations, we do. The equations are our way of describing regularities we observe. The path integral isn't the universe's internal monologue, it's ours. And that's okay. So where does this leave us? Not with a tidy answer, but with a better way of thinking. The next time you imagine a particle moving, don't picture a single clean trajectory carved into space-time. Picture a cloud of possibilities, most of them canceling, a few aligning, and one outcome emerging not because it was chosen, but because it survived the math. That shift from selection to interference is the heart of Feynman's contribution here. If there's one thing to take away, it's this. Understanding doesn't come from memorizing which path wins. It comes from seeing why the others lose. And if you want to really test whether you've understood the idea, try this. Take a simple motion you think you understand, a tossed ball, a beam of light, an electron in a wire, and ask yourself how the path integral would explain it. Which paths would reinforce? Which would cancel? What changes if the conditions change? If you can play that game honestly, even roughly, you're thinking in the right direction. That's all Feynman ever asked for. Not reverence, not certainty, just the willingness to follow an idea wherever it leads, even if it sounds a little crazy at first, because sometimes the crazy idea turns out to be the simplest one after all.